Hello, my name is Jason Anderson. I'm from the LegUp High-Level Synthesis Group at the University of Toronto. This video gives a demo on how to use the LegUp HLS tool. We will synthesize a circuit that computes the Mandelbrot set. Let's first take a quick look at the C code involved that we're going to synthesize to hardware. As you can see here, we have a function Mandelbrot, and two loops are highlighted, for j and for I. The first loop, for j, walks over each row of the Mandelbrot image. The second loop, for I, walks over each pixel in a row. Then there's some initialization of variables that correspond to the real and imaginary part of a number. And the main inner loop, which is actually doing the heavy computational work, is shown here for iter. And what you can see, this contains a number of fixed point multiplies and addition operations. And this loop runs for maxiter iterations. At the end, we compute the color of the particular pixel. And we keep a track of the number of pixels that have escaped from the Mandelbrot set, and this is used to verify correctness. Now let's take a look at the main function. The main function, as you can see, makes a call to the Mandelbrot function that I just showed you, and it also incorporates some correctness checking. In particular, we count the number of pixels inside and outside the Mandelbrot set, and we report pass or fail. Before we synthesize that to hardware, let's run it in software. Compile it with GCC, run it. We see count 2989 and a pass. So it passed in software. Now let's synthesize that to hardware using LegUp by typing make. That produces a file mandelbrot.v, which is the Verilog file containing the LegUp synthesized hardware for the mandelbrot.c file that I showed you. Let's open up the Verilog. It's a long file. I'll just highlight one aspect to you. At the end of the file, there's a test bench. And what you can see in the test bench here, we instantiate the generated Verilog circuit, which is called top. The test bench also stimulates the circuit with a reset and clock signals and so on. And it incorporates several $display statements shown here that report the return value of the circuit as well as the number of cycles it takes for the circuit to execute. Now the next step is to bring up the LegUp GUI and gain some insight into the hardware produced by LegUp for that software. So we start the schedule viewer and we pass in the scheduling report produced by LegUp HLS. When you do that, you'll see an image like this, which is the call graph of the program. Here you see the main function calling printf. If we double click on main, we can see the control flow graph of the program. Each node here represents a basic block, which is a chunk of straight line code with a single entry and exit point. And the edges between nodes correspond to control flow in the program. This one highlighted here is actually the innermost loop of the Mandelbrot computation that we looked at earlier with the fixed point multiplies and adds. If we double click on that, we can see the schedule and as well as the computations in that basic block. In the middle panel here, you see what looks like assembly code. That is actually the LLVM compiler's intermediate representation of the program. On the right-hand side here, in this panel, you see the LegUp schedule for those computations. In particular, you see the clock cycle in which each computation has been assigned. Now notice the colors right here. What we've implemented is that if you mouse over one of these colored boxes in the schedule, we show you the input and output dependencies of that particular instruction. Here we're looking at a multiply instruction, and we see its input dependencies shown in red and its output dependencies shown in yellow and orange. Now the next step is we'll simulate that hardware using ModelSim. We type make v to do that. And we see the result of that. We're getting a count of 2989, the circuit pass, so hardware is functionally correct as far as it's computing the correct value, the same value as software. We also see the number of cycles, 759,000 cycles it took for the hardware to complete its execution. Now we can compile that into the Altera Cyclone 2 FPGA. It's a 90 nanometer FPGA. To do that, we type make P and make F. And that video there was actually sped up. The Altera tools don't actually run that fast. Having compiled it into Cyclone 2, we can look at the static timing analysis report produced by Altera. And we can see that the circuit implementation of Mandelbrot runs at about 108 megahertz. can also look at the area consumed by the circuit implementation. We bring up the Altera Fitter report. We see that that circuit implementation took about 2,500 logic cells and 24 multiplier elements. A logic cell in Cyclone 2 comprises a 4-let flip-flop pair. You can enter that into a table. We have the cycles, clock frequency, wall clock time, which is the cycles times the clock period, number of logic elements, and multipliers. Next thing I'm going to show you is how to apply loop pipelining in LegUp. We're going to pipeline the innermost loop of the Mandelbrot.c that we looked at earlier. Let's bring up the Mandelbrot.c file again, and let's go to take a look at that innermost loop where we were before. I want to point out that in each iteration of this loop there's actually a loop carry dependence. Okay, so there's data in one iteration of the loop depends on data in the previous iterations of the loop. Now to pipeline this loop, what we will do is we'll add a label in front of this for statement right here. And we're going to use that label later in a tickle file to invoke loop pipelining. So we add a label here called, let's call this loop loop, and we put a colon there, so we're adding a label in C. Then we bring up the tickle file, config.tickle, and we add a statement in the tickle file, loop pipeline, and then we put the name of the label that we just added to the C right there. So that will invoke loop pipelining for that loop. And that's it. That's how to do loop pipelining in LegUp. Now, what we'll do now is we'll recompile that, we'll resynthesize it with LegUp, and we by typing make, and we bring up the loop pipelining report produced by LegUp. And as you can see here, loop pipelining was successful for that loop, and it achieved an initiation interval of 2. That means every iteration of the loop can start every 2 clock cycles. And with loop pipelining, of course, we're exploiting parallelism, loop-level parallelism in the circuit. What we'll do next is we'll reopen up the GUI, the schedule viewer, and we'll take a look at the schedule for that pipeline loop. And what you can see here is a display of the loop pipeline schedule. You see iteration of the 0 of the loop executes for 2 cycles, and then in the 3rd cycle here, iteration 1 of the loop commences. So we are overlapping the execution in hardware of 2 iterations of the loop. So indeed we have some loop-level parallelism. Now we'll type make v to simulate the circuit with ModelSim. And as you can see, we're still getting the correct answer, count 2989. So we're matching up with the software. Cycle count has been reduced. We now have 560K cycles. So loop pipelining indeed was helpful in reducing the cycles of the circuit and improving its computational throughput. Now we'll compile that into the Cyclone 2 FPGA, bring up the static timing analysis report. The circuit still runs at about 108 megahertz, so we haven't really lost any clock frequency. Let's look at the area consumption in the Altera Fitter report. As you can see, logic elements 2,500 and embedded multipliers 24. So we haven't seen a appreciable change versus the first implementation. You can fill in our table. What I can point out here is that wall clock time has been reduced on account of the cycle count being reduced versus the initial implementation. So indeed, loop pipelining helped us to get better wall clock time for this circuit. The last thing I'll show you is the pthread support in LegUp, how we can convert parallel software into parallel operating hardware by using pthreads. Let's bring up the Mandelbrot.c again, and you can see we've changed the function signature of the Mandelbrot function to take a pointer to the thread data. The way this is going to work is we're going to instantiate 4 Mandelbrot cores, and each is going to be operating on a certain set of rows of the image. In fact, 1/4 of the rows of the image. So each core is doing different work, and Mandelbrot is a very data parallel operation. Start index and max index correspond to the rows that this particular thread is responsible for. At the end of the Mandelbrot function, you can see we are returning back the count of the number of pixels that have escaped the Mandelbrot set as before, so we can do correctness checking. In the main function, we now see the familiar pthread create and pthread join. These are the standard functions from the thread library, C's thread library, and we will convert parallel operating hardware from these p-thread forking of threads right here and joining of threads. In this case, as I said, we'll instantiate 4 Mandelbrot cores. What we'll do next is we'll run that in software. So we compile it with GCC, still getting the correct answer, 2989. Now let's compile that with LegUp, do high-level synthesis by typing make parallel, and we'll simulate with ModelSim by typing make v. We are still producing the correct answer, 2989, so the hardware looks correct. What I want you to notice here is the cycle count has been reduced by a whole lot. We now have 109K cycles by exploiting spatial parallelism in the hardware. I'm not going to show the Altera implementation results just for the interest of time. Filling in our table, you can see that actually the Fmax has dropped in the parallel implementation. Wall clock time is really improved, down to 1.5 milliseconds. Logic elements is a much more because we have parallel implementations of Mandelbrot, and our multiplier count has also increased a great deal. If we look at area delay product, pipelining is the best area delay product. However, if one cared really about computational throughput, one would probably opt for the pthreads implementation. And I also want to mention that this is part of a lab available on the LegUp website, which includes several other pieces, where we change the multiplier latency assumed by LegUp, and a second one where we apply some loop transformations. In particular, we interchange the second and innermost loop of Mandelbrot. What you can see in so doing, we can get the best area delay product with the loop transformations. So I encourage you to go try the lab on the LegUp website. Thank you very much for listening to this.